Welcome, everyone. Today, we're going to uncover the hidden mathematical architecture of the physical world. We're literally deconstructing dynamic systems to show you the elegant math that binds everything, from heating elements to pressure tanks together. It's going to be a fascinating ride.
Oh, and before we jump into the thick of it, a quick credit to our producer, Tahia Kanande Dr. Nima Madian. I'm absolutely thrilled to welcome you to this explainer on modeling dynamic systems. Specifically, we'll be focusing on first-order thermal and pneumatic frameworks today. By the end of our time together, you won't just look at heaters and pressure tanks the same way. You're going to actually see the foundational equations that govern their very existence.
So here's our roadmap. 1. Foundations of system modeling. 2. Thermal systems and heat. 3. Pneumatic systems and pressure. 4. Deriving the dynamic equation. And 5. The universal mathematical model. Basically, we're going to conquer the math behind two seemingly totally different physical worlds to reveal their shared structural skeleton.
Section 1. Foundations of System Modeling. Okay, let's establish our ground rules. Everything we do in control engineering relies on one really fundamental, almost philosophical act. We have to abstract a highly complex physical reality into manageable, bite-sized mathematical formulas.
Because, in reality, nature's messy. Thermal properties are distributed, meaning temperature varies continuously across the physical body of an object. And sure, that's beautiful in nature, but computationally, it's a complete nightmare for simple control systems. So, engineers make a strategic compromise. We abstract that complex reality into what we call a lumped parameter. We essentially pretend the entire object has just one uniform, concentrated temperature, represented by a single value, theta. This singular lumped parameter is exactly what makes precise control modeling possible in the first place.
Section 2. Thermal systems and heat. With that foundational mindset established, let's transition into our first physical domain. And hey, don't worry, we're going to start by building a rock-solid foundation in thermal mechanics before we make things too complicated.
Right, so everything in a thermal system essentially comes down to how heat flows. The heat flow rate, that's Q, is directly proportional to the temperature differential, delta theta, multiplied by our constant K. Heat flows via physical touch, which is conduction, or through moving fluids and gases, which is convection. But wait, what about radiation? Well, because we're usually dealing with relatively small temperature differences in these control systems, radiation's nonlinear impact is pretty negligible, so we actually just ignore it to keep the math clean and functional.
And that brings us to our first major parameter, thermal resistance, or R. Simply put, resistance is the change in temperature differential divided by the change in heat flow. It's the inverse of our constant, so R equals 1 over K. But keep in mind, the geometry of your system totally changes how you calculate this. For conduction, say through a solid block, resistance relies on the thickness, delta X, divided by the material's thermal conductivity and surface area. But for convection, like wind blowing over a plate, it's simply 1 over the convection coefficient times the area. The physical mechanisms differ, yeah, but they both give us that absolutely crucial value, R.
Moving on, our second vital parameter is thermal capacitance, labeled C. Now, if resistance is all about opposing flow, capacitance is about storage. It's defined as the ratio of the change in stored heat to the change in temperature. The elegant formula we use here is C equals M times C. That's the mass of the substance multiplied by its specific heat capacity. It tells us exactly how much thermal energy an object can absorb before its temperature rises by 1 single degree.
To see this in action, let's look at a real-world system, the stirred tank heater. We've got cold fluid entering, a heating element adding thermal energy, and hot fluid exiting. But to model this using the math we just covered, we have to enforce two really rigid assumptions. Number 1, perfect insulation. Zero heat escapes through the walls into the environment, literally none. And number 2, perfect mixing. That motorized agitator must instantly and completely mix the fluid so the temperature is perfectly uniform throughout the whole volume. Remember that lumped parameter we talked about earlier? This is exactly where we apply it in practice.
Section 3. Pneumatic systems and pressure. Okay, we've mastered Domain A. Now brace yourselves, because we are shifting this explainer entirely over to Domain B, pneumatic systems. While our foundational control logic definitely survives this transition, the physical definitions you just learned are about to undergo a pretty radical change.
Let's take a second to contrast the core drivers of these two domains. In the world we just left behind, heat flowed because of a temperature difference, right? But in the pneumatic world,
Fluids and gases flow strictly because of a pressure difference. We're essentially swapping out the thermometer for a pressure gauge.
Think about a spherical vessel. Here, mass movement isn't driven by heat at all. It's driven entirely by delta P, the pressure differential. If the pressure outside is higher than inside, gas flows in. If it's lower, gas flows out. The fundamental architecture of our control logic remains totally intact, but we're now mapping it onto entirely different physical phenomena.
But here's where we hit our main mathematical conflict for today. Unlike straightforward thermal resistance, fluid resistance behaves non-linear. Resistance actually fluctuates depending on the current state and pressure of the system. This curving non-linear relationship between pressure and flow makes simple algebraic modeling pretty much impossible. So we need a mathematical intervention.
And that intervention is called linearization. It's a foundational trick in control engineering. We're essentially taking a messy, nonlinear reality and approximating it as a clean, linear system. But, and this is key, only around a very specific, normal operating equilibrium point.
To actually solve this, we isolate that normal operational equilibrium point. You know, that sweet spot right in the middle of the curve where the system usually runs, by drawing a straight tangent line through it and sticking to microscopic deviations around that point, which we label lowercase p and lowercase q, we can safely pretend the system is linear. So our fluid resistance, R, becomes simply P divided by Q. It's an approximation, sure, but it is an incredibly powerful one that totally saves our mathematical model.
Just like in thermal systems, pneumatics also have capacitance. Here, pneumatic capacitance is the change in stored gas mass relative to the change in gas pressure. The general equation involves volume, V, and specific weight, L. However, for ideal gases, where temperature is strictly constant, C simply becomes the volume divided by the gas constants times temperature. Once again, it's really all about how much stuff, in this case gas, a container can hold before the pressure spikes.
Let's apply these new pneumatic principles. Imagine a pressure vessel. We have an inlet flow facing some resistance R, filling up a tank with capacitance C. To model this, we rely on the fundamental law of conservation of mass. The capacitance, C, multiplied by the rate of change of the output pressure over time, that's dPo over dt, must exactly equal the rate of gas, Q, being added to the vessel. Because, as we know, mass can't just magically appear or disappear.
Section 4. Deriving the dynamic equation. Excellent. We've gathered all the necessary components from both physical domains. Now it's time to forge them together into one unified, functioning mathematical structure.
Merging these concepts is actually pretty straightforward. We start with that mass conservation law we just discussed. C times the derivative of output pressure equals Q. Next, we bring in our linearized flow equation from earlier. Flow Q equals the pressure difference, that's inlet minus outlet, divided by resistance R. Now we just substitute that second equation into the first one. After a bit of basic algebra to clean it up, we arrive at the combined formula RC times the derivative of the output pressure plus the output pressure itself equals the input pressure. This right here is the combined first-order differential equation. It flawlessly describes the dynamics of the system over time.
But here's the catch. Differential equations can be a real headache to work with when you're designing complex control loops. So we execute a vital shift. Applying the Laplace transform shifts our model entirely out of the time domain, represented by dt, and straight into the frequency domain, represented by the variable s. Suddenly, our complex differential equation beautifully condenses into this pristine, elegant building block, 1 over RC plus 1. The output divided by the input simply equals 1 over RC plus 1. Honestly, this is the holy grail for a control engineer.
Section 5, the universal mathematical model, which brings us to the climax of this explainer. We've looked at heat, we've looked at pressure, but now I want to prove to you that these vastly different physical worlds are, secretly, identical under the hood.
Look, when we compare the two systems side by side, the physical realities are completely different. In a thermal system, the driver is a temperature differential. In a pneumatic system, it's a pressure differential. The flow is heat flow versus mass flow. The geometry relies on physical area versus physical volume. And storage relies on mass and specific heat versus gas constants. Totally different, right? Yet, they both share the exact identical transfer function, 1 over RC's plus 1. While the physical definitions differ entirely, their transient behaviors in a control loop are mathematically indistinguishable. It's basically magic.
This mathematical skeleton is universal for first-order systems, which leaves us with a pretty provocative thought to end our session. If thermal systems and pneumatic systems secretly share this exact same mathematical DNA, what about electrical circuits? What about complex mechanical spring mass systems? I'll leave you to ponder just how deep this universal architecture truly goes. Thank you for your immense focus today. This concludes our explainer. Keep questioning the physical world around you.